Today we're going to be talking about rates of change in tangent lines. And we started talking about rates of change in a previous section, in the first section of this chapter, but this is also laying the groundwork for everything we're going to be doing for pretty much the rest of the year. So the average rate of change. So say we have some function, and I have an a value, I have a b value, and I have the line that goes through those 2 points. The average rate of change is the slope of the line that goes through those 2 points. We often call that the secant line, and that's going to come in play in a later chapter. And so to find the slope of this line, let's call this f of a and f of b. So my slope is y2 minus y1 over x2 minus x1. So all we're really doing is slope when you're doing the average rate of change. Is a slope through 2 points. So find the average rate of change for the function over the interval. Okay, so f of 2 is equal to 8, f of 1 is equal to 1. So I do f of 2 minus f of 1 all over 2 minus 1, 8 minus 1 over 2 minus 1. That is going to be equal to 7. Now a tangent to a curve. This is so important. This is the basis of everything we're going to be doing. So the tangent to a curve. So say I'm trying to figure out the tangent at this curve x. What's the slope of the tangent to this curve? So what we do is we go over some certain amount of x. And then, so therefore we have f of x and we have f of x plus h. Okay, because I went over some h, so this is whatever x value that was plus h. So if I find the average rate of change of this secant line, okay, so if I find the average rate of change, it's what we just did, y2 minus y1. Over x2 minus x1. This simplifies to f of x plus h minus f of x all over h. But a tangent line is a line that hits our curve not at 2 points, but hits it at exactly 1 point. That hits at x, and then that's it. Okay, yeah, if I extend the line, I extend the curve. I don't know what my curve does. Could hit it at some point over here, but it hits this x at 1 point. So how do I bring this slope of this line infinitely close to getting to the slope of this line? I add in a limit. The limit as h goes to 0. Because as h goes to 0, this point's going to slide down my curve and get infinitely close to x, so this green line and this purple line are going to end up being the same thing. So a tangent line, it hits at exactly 1 point, okay? And the slope of that tangent line is a limit. That's why we learn limits, so we could get the slope of our tangent line. Now the normal line is perpendicular to our curve at the point of tangency. So you find your slope. Let's see. So you find your slope of your tangent line using this formula, and then you do the opposite reciprocal. Okay, so finding the slope of the curve. So it's just a whole bunch of algebra from here, guys. Limit as h goes to 0 of f of x plus h minus f of x all over h. So this is the limit as h goes to 0. Notice how I keep writing that limit. X plus h squared minus f of x. I'm going to put that f of x in parentheses so I don't forget to distribute the negative. Now I realize writing that I made a little mistake. I need to add in my plus 1 all over h. Okay, doing my algebra. Okay, now from here, what's nice? Some terms are going to cancel. Things should cancel. And then you should get something so that on the top you can factor out an h so that that h on the top is going to cancel with the denominator. So that you're going to get this. When I plug in 0, we get 2x. This is standing for the slope at any point. So the slope of any point on this curve is 2x. But we're looking for our slope at x equals 4. So our slope when x equals a negative 4 is negative 8. So I'm going to do y minus y1 equals m times x minus x1. Plug in negative 4, and I get a 17 out. Now finding the slope of the curve of the normal line. So the slope of our tangent line was negative 8. So our normal slope is going to be 1/8. So you do y, it's the same point. So I have the same coordinates of negative 4, 17. Y minus y1 is equal to m times x minus x1. Instantaneous rate of change of a particle's position. Okay, this is the same thing. Just now instead of f of x plus h, I have f of t. So the slope at any point for this function f of t is f of t plus h minus f of t all over h. So it's the same thing. So I'm looking for the instantaneous rate of change. Instantaneous rate of change, okay, that's a limit. For the volume of a sphere, our volume formula, 4/3 pi r cubed when our radius is 2. So we'll do the radius is 2 at the very end. So you set up your limit formula. Limit as h goes to 0 of 4/3 pi r plus h squared minus, cubed minus 4/3 pi r cubed all over h. Now it's honestly a bunch of algebra. Foiling that out. Since both terms have a 4/3 in them, I'm going to factor that out and put another bracket in here so that I have just an r cubed here at the end. So I factored out that 4/3. Just to make my life a little bit easier. Now notice what cancels. R cubes cancel. I just told you, let's do this. The r cubes cancel. Now I can factor out an h from each term so that I'm left with 3r squared plus 3rh plus h squared all over h, so that now my h's cancel. Now, find the limit as h goes to 0. Well, any term that has an h in it is going to go to 0. So, our resulting formula is 4 pi over 3 times by 3r squared, which simplifies to 4 pi r squared. Now, I need to find it. This is for any instant. So once I found this formula, I can have an infinite amount of these r's. But I just need it when r equals 2. So when I plug in r to be 2, when I plug in 2, we get 2 squared is 4, 16 pi. Okay. Please, for me, make sure that you fill in the Google form that is located right behind this video, and please make sure that Google form is submitted on time.